Hello everyone, this is Narzo Tarannum and welcome back to the CSE 321 Operating System course lecture. In this video segment, we are going to discuss about deadlock avoidance method using Banker's algorithm. In previous lecture, different deadlock prevention techniques were discussed by limiting how requests can be made, which ensure that at least one of the necessary conditions for deadlock cannot occur. And the possible side effects of this prevention method are low device utilization and system throughput. So now we will discuss about the deadlock avoidance technique. So the deadlock avoidance technique is an alternative method for avoiding deadlocks is to require additional information about how resources are to be requested. Means system does not put any restriction on the way a process request for the resources, but the system will decide whether the request will be immediately granted or the process have to wait for the release of the resource that hold by other process. Here process P, we can see in the figure that process P requesting for two instances of resource R. Suppose all three instances of resource R are available, but before allocating the resource, system will check whether there will be any deadlock in the system for this allocation or not. That means system will check whether it is safe or unsafe in advance. A method for avoiding deadlock requires that the operating system have a prior information about how each process will utilize system resources. For example, Banker's algorithm requires a priori information about the maximum number of each resource type that each process may request. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. And the third one is the resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. So the system decided in advance if allocating a resource to a process will lead to a deadlock. Now the next question, is there any algorithm that can always avoid deadlocks by conversely making the right choice? That is, can we ensure that the system never reaches an unsafe state by making some choice in the way processes execute or the resource also allocate and so on? So there is an way we can build such an algorithm is by using what is known as a Banker's algorithm. When a process requests an available resource, system must decide if immediate action leaves the system in a safe state. Now, what is safe state? A state is said to be safe if there is some scheduling order in which every process can run to completion. That means system is in safe state if there exists a set sequence of all process. On the other hand, an unsafe state does not have to lead to a deadlock. It could lead to a deadlock. We must ensure system never reaches an unsafe state. Here an example of safe unsafe state will be discussed. This concept will be needed for Banker's algorithm. There are three processes A, B and C. And the system has total 10 units of resource. Using this resource, processes have to finish their work. In advance, every process has to declare the maximum number of resources they needed. Here we can consider the table with three processes A, B and C, and each process already has some unit for their work. So at this time of instance, A has got 3 units, B has got 2 units and C has got 2 units, and there are a total number of 7 units given. Though there are total 10 units here in the system, so 3 units of resource in the system is remaining, or we can say free now, and not allocating to any of the processes. On the other hand, the maximum requirement for each process is 9, 4 and 7 respectively. These maximum requirements are declared by the process in advance. Now, using this particular table, the system should be able to allocate the maximum units to processes in such a way that no unsafe state is reaches. So let's see the example in next slide. So the problem we are trying to solve here is whether these allocations maximum of 9, 4 and 7 can be made to A, B and C in such a way that the state is safe. Let's start with 2 units being allocated to B. So we have 3 units in the free store. Out of these 3 units, 2 are allocated to B. Now B has 2 plus 2, that is 4 unit, and the free store now become 3 minus 2, that is 1 unit. So in free storage, we have now remaining 1 unit only. Now after B completes, all the 4 units of B are returned to the free store because the work of B is done. So 4 plus 1 will be 5 units present in the free store now. So the amount of resource B using for their work, they will release the resource after their completion of work, and the released resource are added up with the in the free storage now. And these 5 units can be allocated to C now. So C will get its maximum limit of 5 plus 2, what is 7 units. As seen over here, the amount present in the free store is 0 unit. Now after C completes, all the 7 units of C get returned back to the free storage. Now the system could allocate the resources required by A. That is, the resources required by A is 6 more units to get its maximum limit of 9 units. So we have 9 units allocated to A and 1 unit which is free now. Thus, we see with this particular start point on the state of the system where there are 3 units are free and maximum of 9, 4 and 7 units as the maximum limits of each process can have. We see that with this particular state there is a schedule which is possible so that all maximum requests by the process can be fulfilled. So we call such a state as a safe state. So here the scheduling order in which every process executes in the following order: first B, then C, and after that A. Now let's look at another example where the state we start with is that A has 4 units, B has 2 units, C has 2 units. A total of 8 units are present with A, B and C respectively, and free unit is 2, and the maximum limits of each process is as before, like 9, 4 and 7 respectively. Now we see that irrespective of how the system tries to allocate these remaining units to each of the process, there is no schedule which is feasible that could fulfill these requirements. For example, suppose B were allocated 2 more units and you can see that there are only 2 units free. So B is the only process which can be served. Therefore, B gets 4 units while there are 0 unit present in the free storage. Now after complete of B, we have 4 units free, but you see that neither A, which requires 5 more units, nor C, which requires 5 more units as well, can be serviced with 4 units. which is present in the free storage. Therefore, we see that this state is an unsafe state because there is no scheduling order which can meet these requirements. So this is an unsafe state. The system banker's algorithm must ensure that such a state is not reached at any point. If we summarize the concept of examples, then we can say a safe state is not a deadlock state. Conversely, a deadlock state is an unsafe state. Not all unsafe states are deadlocks. We can see this in the figure. So we can say that an unsafe state may lead to a deadlock. So what we talk about now is Banker's algorithm of deadlock avoidance approach. When a new process enters the system, it must declare the maximum number of instances of each resource type that it may need it. We must remember that this maximum number may not exceed the total number of resources in the system. When a user requests a set of resources, the system must determine whether the allocation of this resource will leave the system in a safe or unsafe state. If it will save, then resources are allocated. Otherwise, the process must wait until some other processes release enough resources. So the system always do some background calculation, and based on the output, it will decide whether a request for the resource are immediately granted or not. So naturally, in case of deadlock avoidance, because the system has to do some background calculation to see how the resources are going to be released by different processes, so it is better to declare the maximum requirement of the resources for each process in the system. But it is not necessary that the process will acquire it before its execution. The process at least let the system know that so many instances of such resource type will be required by the process while execution. If that is known by the system, then it is possible by the system to see whether the resource can be allocated or not. So the main things we need to remember whenever using Banker's algorithm is multiple instances can have of each resource type, and each process must priori claim maximum use of resources. When a process requests a resources, it may have to wait. And the last important point is when a process gets all its resources, it must return them in a finite amount of time after their completion of work. The name of the algorithm was chosen because the algorithm could be used in a banking system to ensure that the bank never allocated its available cash in such a way that it could no longer satisfy the needs of all its clients. Several data structures must be maintained to implement the banker's algorithm. We need all this data structure where n is the number of processes in the system and n is the number of resource type. And as we have said, every resource type can have a k number of identical instance of that resource type. So the first data structure is available, which is a vector of length m. If a available j is equal to k, then k instances of resource type rj are available. That we have to understand it by this available data structure. Or also we can say that available is a vector. And the second data structure is max, which is a two-dimensional array, defines the maximum demands of each process. If max ij is equal to k, then process pi may request at most k instance of resource type rj. And the third data structure is allocation, also an 2D array of n into m, defines the number of resources of each type currently allocated to each process. If allocation ij is equal to k, then process pi is currently allocated k instance of resource type rj. Now, the fourth data structure is need, which is also an two-dimensional array of n into m, indicates the remaining resource need of each process. If need ij is equal to k, then process I may need k more instances of resource type rj to complete its task. Remember that need equals to max minus allocation, which can be computed from max and allocation matrix, which are given in the example or in the system. Now some notation we need to know that is, if x and y are two vectors, in that case if we assume x is less than equals to y, if every component of x is less than or equal to the corresponding component of y, so this is how, here is an example given of x and y. So this is how we can compare these two vectors, where each component of x is compared with each component of y. And here for the value of x and y are not equal, or we can say x is not less than equal to y. We will now present the safety algorithm for finding out whether or not a system is in a safe state. So the safety algorithm used to local data structure work and finish. Work is initialized by data structure available, and finish is a Boolean vector. All the components of finish are initialized to false. Then the algorithm works like this. You find a process I for which finish I is equals to false and need I is less than or equal to work. You find here work is initialized as available. If I get a process for which need I, that is the future requirement of the process, can be made by presently available resources, we ensure that the process can be completed in the present state following some sequence. Now, if the second line is completed, then we come to the next step, that is once this process is completed, then all the resources we are currently allocated to it, they will be released. So work is nothing but the available resource now, which is incremented by the allocation Ri, and simultaneously finish I is made to true to increasing that the process is complete. Then go back to the step number 2. These 2 and 3 number state will have a number of loops. At some point, if I find that I cannot get any I for which need I is less than or equal to work, or nor finish I is equal to false, so this may happen by one of the two reasons, that maybe for all the component is finish and finish I become equal to true. So that is one condition. And the second case, maybe the finish I is equal to false, but need I is, because the need I is greater than equal to work. Okay, whenever be the case, we come to the step number 4. In step number 4, we check if finish I is equal to true for all I, and this is the case when all the process can complete following a sequence. When the system is safe, but if finish I is not equal to true, at least for one I, that means that process from the current state cannot finish any of the sequence. But if I get finish I remains false for some process, we will say the state is unsafe. And as we say that unsafe state does not means that this will be deadlock, but indicate that there can be a deadlock. So we never want to take that risk. Let's take an example to illustrate this algorithm. Suppose in a system we got three types of resources A, B and C. We assumed here that A has got 10 instances of resource, B has 5 instances of resource and C has the 7 instances of the resource. So these are the resources that we have in the system. We assume at a particular instance of time there are 5 processes in the system who wants to share those resources, and we name this process P0, P1, P2, P3 and P4. Now, two matrix allocation and max will be given here, and a vector available will also be given. Though there are three different resources, so we have three different columns for them, and the 5 processes are given here. So this table will be given. We can see here for P0 has been allocated 0 instance of resource A, 1 instance of resource B and 0 instance of resource C. Whereas the maximum number of resources for process 0 is 753. Simultaneously for all the process, the allocation and maximum requirement will be given here in the table. To compute the available number of resources, we have to add up all the resources which are allocated to different process. To compute the available number of resources, we have to add up all the resources which are allocated to different process. At this instance of time, the total number 7 instances of resource type A are given to different process. And the maximum number of resource of type A which is available is 10 in the system. So out of 10, we have already 7 number of instances given to each processes. So in available, we will have now 10 minus 7, that is 3 instances of resource type A are available. Similarly for B type of resource, total 2 instances are allocated and maximum 5 instances are available in the system. So the available for resource type B is 5 minus 2, that is 3. That is 3 instances of resource type B are available. And for C, 7 minus 5, that is 2 instances are available. So this becomes the available vector. Now for applying Banker's algorithm, we need to calculate need matrix. Need is simply the difference of max and allocation. The need matrix at this particular instance of time is, for P0, we find that the maximum requirement is 753, out of which allocated is 010. That means need will be 753 minus 010, that is 743. In similar way, we calculate P1, P2, P3 and P4. So this is our need matrix which we calculated from our given maximum and allocation data structure. Now we want to find out whether the state that we reach is a safe state or not. That means we That means we will find it using banker safety algorithm. So in this slide, for our convenience, I put the algorithm on left side and all other data sets for the example on right side. In banker safety algorithm, what we have done is we have taken data structures that is what is initialized by available. And in this case, available vector is 332. So work is initialized to 332. And there is another data structure that is finish. Since there are 5 processes, so this vector finish will also be of dimension 5. And initially, all the finish vector is equal to false. Now for banker safety algorithm, we have taken every process and try to find out whether the future need of the process can be satisfied by the available number of resources at that instance of time. Now let's try to see this. We have current available resource is 332 and the future need of process P0 is 743. So P0 cannot be completed with this available resource at the first time. So finish I for P0 will remain false for the first go and that can be modified later. Now whatever for P1 its future requirement is 122 and the available number of resources is 332. So we find that 122 is less than 332. So P1 can complete operation and we can say finish 1 is equal to true and work will also update by the allocation of P1, that is work equal to work plus allocation of P1, because when P1 completed its task it will release all the allocated resources of it. Here the allocation of P1 is 200. So work will be incremented by 200. Now the current work vector become 532. Now with this available resource we come to P2. The future requirement of P2 is 600, which is not less than or equal to the current available vector, that is 532. So P2 cannot complete and remain false. Come to P3. The future requirement of P3 is 011, which is less than or equal to our current available. So P3 become true because it is completed and will return its all allocated resources to the available vector. Now the modified work will be 532 plus 211, which is the allocation of P3. So the current work vector become 743. With this we will come to P4 and the future need of P4 is 431, which is less than current available vector. So P4 can complete and become true. Work will also updated by adding up the allocation of P4, that is 743 plus 002 is equal to 745. So this is the available resource after completion of P4. I will go back again. Find future requirement for process P0 will be 743, which is less than or equal to of our available resource at this instance of time. So now P0 can complete making finish finish 0 equal to true and work will also be modified by adding up the allocation of P0. So work will become 745 plus 010, which was the allocation of P0, now become 755. Now with this 755 of available resource, we will come to the process P2 because P1 already completed. P2 could not be completed at the first go. So now we come to process P2 whose future requirement is 600, which is less than or equal to our current available 755. That is, P2 is completed, making finish 2 is equal to true, and work will be modified and become 755 plus the allocation of P2, which is 302, is equal to 1057, and it is quite natural that it is the same number of the maximum number of resources in the system. That is, A has total 10 number of instance, B has total 5 number of instance, and C has total 7 number of instance. And after finishing all the processes in a system, all the process release the resources, and we have remain the same number of resources. So we can say that the process is successfully processes are successfully completed its work. So we find here all the process can complete in a sequence, and the sequence is P1, then P3, then P4, P0 and P2. And this is the one that we calling at a safe sequence. So the safe sequence for this state is this. Now, because safe sequence exists in the system in this particular state, so the system is safe. So we can conclude the banker's safety algorithm here. Remember, this is not only the unique safe sequence in the system at this particular state. Here we started our scanning from P0, that's why we got this sequence. But if we start it from the reverse order of the process, the safe sequence will be changed or different for this algorithm. So the safe sequence in a state of a system is not unique. However, if at least one safe sequence exists in the system, then we can say the state is safe. Now, once we are in a safe state, and if a process put a request for some number of resources at this state or at this stage, then what will happen? Then we have to check whether this request can be immediately granted or not. Suppose process P1 requests for the resource 102 currently. Now the banker's resource request algorithm will be executed whenever a process puts a request, and we assume the request is always made as a form of vectors, where every element in that vector will be indicate how many instances of resource type R is requested. So whenever process Pi puts a request, now the algorithm is this: whenever a process Pi puts a request, then the request can be made only when request I is less than or equal to available. Available tells that what are the number of resources that are currently available in the system. Then if request is not less than or equal to the available resources, then obviously the request cannot be made. So the process has to wait. And the other condition is other condition and the other condition is whether request I is less than equal to its corresponding need vector or not, so that the request must not contradict with the maximum number of resources that is declared in the beginning. So the first condition will have to check whether it is valid request or not. So in the first step of the algorithm, it will check if request I is less than equal to need I, then I said need I, that is the ith row in the matrix need. If this is true, then we only proceed the request to the step 2, else an error message will be given. Now, when we come to the second step, it is sure that the request is a valid request. So, in the step 2, we will check whether the request will be immediately granted or have to wait. So, the second check is if request I is greater than available vector, then it has to wait, though it is a valid request. We checked earlier. If request I is less than equal to available, then we go to further step 3, else we have to wait. Up to this, it means that the system is in a position to meet the request. Now the system will pretend if the request will be immediately granted, then it checks if the system is safe or unsafe state. So in step 3, system pretend to allocate requested resources and that modify the following data structure. If the request is granted, the first data structure will be changed is available, and available will be reduced by the request I. Next data structure is to be modified is allocation of I. That is the ith row is the allocation matrix. So the allocation will also be changed, that is added by the request I. And the third data structure that is to be modified is need of I, because need I will be reduced by the amount of request I. So the change data structure are available equals to available minus request I, allocation I is equal to allocation I plus request I, and need I is equal to need I minus request I. So it is the pretension, not the physical allocation. Now we have to see the new state that is arrived in a safe state or not. And now we have to see the new state that is arrived in a safe state or not. And we already know when we call a state is safe, that is whenever every process in the system can complete their task in some arbitrary order. In order a state to be safe, there will be a safe sequence. So in fourth step of algorithm, it checks if this new state is safe. If a safe sequence exists, that is here it will run the banker's safety algorithm, and if we find a safe sequence in this current state, then the resource will be actually or physically allocated. If we find that this new state is not safe, in that case you cannot allocate the resources physically, so you have to restore the previous state by modifying the data structure. So we assume that P1 is request for resource 102. In this slide, for considering this request, we need banker's resource request algorithm that given left side of the slide, and current data structure set are given to the right side of the slide. Now we have to check here whether this request can be granted or not. In first step of the algorithm, we need to check whether this request vector for process P1 is less than or equal to need or not. If it is not less than equal to need, then the request will immediately abort it. So we find here future need of P1 is 122 and it has requested for 102, which is less than or equal to the need. That means this is a valid request. Now we have to check whether the request for P1 is less than or equal to our current available vector or not. In this case, available vector is 332. So 102 is less than or equal to 332. So the system are in a position to allocate these resources. Now in step 3, it will pretend that suppose the resources are allocated by modifying the data structures, and modified data structures are available, allocation and need. Now we get new available vector, that is 332 minus 102 is equal to 230. Then allocation P1 will change, that is 200 plus 102 is equal to 302. Here 200 was allocated earlier or the previous allocation of P1. And if the request for P1 is granted, then allocation will increase by the number of the resource requested by the P1. That's why similarly need for P1 will also decrease by the number of the resource requested by P1. So previous need for P1 was 122. The new need vector now become 122 minus the new request of the resource for P1, that is 102, and now it's become 020. Here the updated table after modifying the data structure is given, where the value of allocation and need for process P1 is changed and the value of the current available is also changed, and all other value for other processes will remain same. So after modifying the state, what we have to do is we will see this state is safe or not. So we have to start the safety algorithm first. So first we check for process P0. Need of P0 is 743 and available is 230, which is less than of need of P. So P0 cannot be completed. For process P1, future need is 020, which is less than available 230. So P1 can complete. After completion, available resource will be 230 plus 302. This 302 is the allocation of P1. So it will now become 532. So this is the current available after the completion of P1. Now come to the process P2. The future need of P2 is 600, which is greater than the current available. So P2 will not complete. Come to the process P3. The future need of process P3 is 011, which is less than current available, that is 532. So the available or work will be updated by the number of the resource allocated to P3, that is 211. Because after completion of P3, it will release all the resources and now current available will become 743. Future requirement of process P4 is 431, which is less than our current available 743. So after completion of P4, new available of or the work vector will become 745. So with this, available 745, I again go back to process P0, where the future need of P0 is 743, which is less than the current available of 745. So P0 can also complete, and after completion it will release the resources that is allocated to it, that was 010. So the current available resource will become 755. With this we come to process P2, because P2 was not completed in the first go. The future requirement of P2 is 600, which can be now made with current available. So P2 can also complete, and on completion P2 will also release the resource 302, which was allocated to it. So available resource after completion of P2 is 755 plus 302 is equal to 1057. And obviously this is the maximum number of resources that are available in the system. And the safe sequence in this case will also same as before, that is P1, after that P3, then P4, and then it will complete P0, and next is P2. Though there is a safe sequence, so this state of the process, though there is a safe sequence, so this state of the process are safe. And because the state is safe, the request of process P1, that is 102, can be granted immediately. However, if we reached any situation that at least one process could not be completed in any sequence, that means the safe sequence does not exist in that particular state, and if the safe sequence cannot exist, the request cannot be granted. Okay, it's your home task. If this is the current state of some process, then a new request 330 for P4 can be granted, and similarly a new request 020 for P0 on the current state can be granted. Listen carefully, these two are separate requests. Thank you everyone for having patience till the end, and best of luck.